Hello guys, hope we're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of electrical circuit. So at this chapter, like the previous one that we were talking about, different kind of method in order to help us to solve any kind of variables and unknowns related to current, voltage, the active power, or some kind of P. At this point, we are going to talk about a new method that we call it as nodal analysis. So without further ado, let's talk about it. So at this chapter, as I just mentioned, we are going to talk about the nodal analysis. Just like the previous one that we were talking about, the mesh analysis, we would like to somehow expand the work and see that what would happen if you're going to use another method. Obviously, having more methods in order to give us more freedom in order to solve the more complex question. So this chapter is going to be a little bit different from the previous one because at this point, I found out it would be better to talk about this kind of definition, talk about this work by examples, because as you guys know about some kind of this method, the only way that you can learn them is through the active learning. It means that you need to have a pen and paper, and whenever you see a question, try to pause the video and then try it by yourself, then come back and replay the video to make sure that your answer is going to be right. So at this point, we are going to do that together, some kind of step by step, and make sure that everything goes okay. Probably I have to make this video into 2 or 3 different chapters because it's going to be long in one long run. So it would be so much fun and it would be so informative. So don't worry about anything. The only thing that I need you guys to know is just make sure that you completely understand the previous videos related to everything towards the electrical circuit, obviously the very basic topics. And at this point, we are trying to see that what would happen if you do have a complex case, when we do have different kind of independent and dependent sources, how actually we can find the current and voltage. So the very first thing that we have to know is about the mindset. As you guys remember, last chapter, we were talking about the very first mindset. The first mindset was about the mesh analysis. Mesh would happen at a time that when you have some kind of mesh, and obviously that mesh is going to be smallest form of loop, it means that you cannot divide that guy into 2 forms, maybe into more than one of its kind itself. It means that at this point, I do have a case that there are 2 independent sources, there are a couple of resistors, and imagine that this guy is going to be another resistor. I just put it over there to show you that it could be any component. I do have my first mesh and I do have the second mesh. I also can consider them as loop, and I know that there is going to be a very big loop. If you guys remember, at some point, we had to use the loop, or we could call this as a super mesh position, especially on the time that we do have a current source inside one of the branches. So we are going to use this analysis, and if we just learned it was good, it was some kind of fast, it wasn't that bad. But what would happen if the condition is going to be more complicated? So on that point, we are going to deal with so many equations. The problem is going to be a little bit unsolvable. I'm not saying that it doesn't have any answer, but probably is going to put so many obstacles on our side. So it would be better to move to the next mindset that we call as a nodal mindset. Unlike the mesh mindset, we are going to focus on nodes. And as you guys know, node is the place that we do have more than 2 connections. So at this point, for instance, when we do have this node, and we are going to work based on the KCL. In the mesh mindset, we were using the KVL mindset. And the nodal mindset, we are using the KCL mindset. So by using the KCL, by using every equation related to currents, obviously we still have to work with the voltages. We can find a voltage at this point and at this point. Then by using that voltage, we can find any variable that we need, especially about the currents. So all in all, mesh analysis is going to be about the loops. Nodal analysis focuses on the critical voltage points, as I just told you, for example, node A and node B. For many complex circuits, the nodal mindset is cleaner, faster, and more scalable. And this Gauntlet is designed to prove it. So as you guys know, whenever we do have more than maybe 2 or 3 meshes, it would be a little bit complicated to solve all of those equations, because probably we are going to deal with 3 equations, 3 unknowns, or maybe more than that. And solving this kind of equation needs advanced mathematical method. That's why it would be better to work on the KCL or work in nodal analysis, which is way better and cleaner. So without further ado, let's start it. At this point, we do have around 15 challenges. I had to get rid of some of them because they were a little bit advanced. So I thought it's not suitable for here, but I would try to focus on more than 10 to 12 challenges and make sure that you guys are completely understanding. So imagine that I do have a case. And at this point, I do have some kind of current sources, I do have my resistors, and I do have 2 nodes. So these 2 nodes are the ones that you're going to choose.
So try to use the nodes that they do have the most amount of connection to them. At this point, I do have node A and I do have node B. This part is going to be ground. So ground is the part that has the most amount of connection to it. As you can see, you have one connection, another connection, this one, and all of them are connected there. We are going to choose the ground as a reference. It means that the voltage at this point, we call it as VG equals to 0, and we can find a relationship between any voltage, between any kind of nodal voltage to this part, and it's going to help us. So the question is simple. The question says that try to solve it for VA and B. It means that the nodal voltage and A and B, and try to compute the current through our A and B direction would be from to here, and then compute the power inside each part. So in order to solve this kind of question, by the way, I do have the answer over here. Again, try to pause the video. So at this point, probably you don't have that much of an idea what's going on, but I'm going to help you out for the first and second challenges, maybe the third one. Try to keep up with me step by step. Then from that point, for more challenges, obviously you have so much idea and you can work on it by yourself. So at this point, I again redraw the circuit itself, and you can see we have two nodes. So why we are going to use the node analysis, by the way, since the very first thing that you can see, we are dealing with the current sources. The current sources is going to help us to use the KCL. And at this point, it will be better to use the node analysis because, as we all know, when we do have the current sources using the KVL, it would be a little bit challenging for us. So let's do the very first assumption that we would get, and maybe most of the textbooks have it, maybe some of them would be a little bit different. But for each node, try to consider that all of the currents is getting out of that specific node. By having this assumption, I can say that the KC at point A is what is going to be accumulation of all of the currents is going to be 0, right? So imagine that the KCL is I1 plus I2 plus I3 equals to 0. So that's the first rule about the KCL. Another thing that we have to consider again at node B be something like this. Till number B, I do have I3, I4 plus I5 plus I6 equals to 0. Maybe some of you would say that, what is happening over here? Because we do have I2, one time move from this point to this point, and we do have I4, which somehow seems the same, but moves from this point to this point. So at this condition, don't worry about it. Just consider that your node is going to be positive all the time. So by considering this fact, you see that at the end, it doesn't matter which direction you use, but at the end, all of those equations are going to help you in order to find the true direction. So far we do have this. We do have two KCL, and obviously we have 6 unknowns and 2 equations. We cannot solve it, right? But another thing that we know is related to our currents. I1 is going to be what? I1 is in the opposite direction of our current source. So we can say that I1 is negative 2 amps. Then move to I2. So what? I2 equals to the current that moves from node A to node B through the 12 ohm. Obviously, we know the current is going to be V, or delta V, divided by R. Delta V means that the voltage that you are here, the voltage of the place that you're going to start your work, subtracted by the voltage at the place of the voltage that you're going to end your work. So as you can see, I2 is going to be between VA, node A, and node B, right? So I'm going to say that I2 is VA subtracted by VB divided by 12. This is another equation. What about I3? I3 equals to the same thing. I do have the node A and I do have the ground. So the difference between those two, it would be VA. By the way, for node voltages, we are going to use voltage, V sign, and index of A, B, C, or whatever node that I'm looking for. So VA divided by 6. So let's talk about the I4. I4 is going to be just like I2, but at this point, we consider VB as a positive voltage. Don't worry about it. I know that now is going to be a little bit confusing, but you will see that the equations are going to actually correct you. So don't worry. So it would be VB subtracted by VA divided by 12. I5 is going to be what? I5 again is going to be in the direction of my current source. I'm going to say that is positive 1 amp. Then I do have I6, which is going to be exactly like I3. So I do have it as VB divided by 3. So far, I do have everything that I need related to the currents. And the only thing that I have to do is just put everything inside those equations, in this equation. So as you can see, we do have VA, VB, and we will have 2 equations, 2 unknowns, so we can solve it easily. So let's do it. The very first one is that I1 plus I2 plus I3 is equal to 0. So negative 2 plus I2 is V subtracted by VB divided by 12 plus I3 is V divided by 6 equals to 0. So I'm going to write down the next one because we are going to move shoulder by shoulder. That would be way better. So this is our first equation. The second equation would be what? The second equation is like this. I do have it as I4 plus I5 plus I6. VB subtracted by V divided by 12 plus I5, which is going to be 1 amp, plus VB divided by 3. This guy equals to 0 itself. Then, since I do have fractions, it would be better to get rid of all of them. How I can do that? As you guys know, in order to get rid of fraction, we have to multiply both sides by the LCD or CD, doesn't matter. So at this point, we consider 12 as our LCD. And at this point, we consider again 12 as our LCD. So we have to multiply both sides by 12. So if we do that, negative 24 plus, if you multiply 12 by this term, you see that 12 is going to cancel this term. So VA subtracted by VB plus 2VA equals to 0. Then I do have another part. I do have the second section, which is going to say that my 12 again is going to be multiplied by this term, but we do have VB subtracted by VA, then plus 12 plus 4VB equals to 0. So we do have it so far. If we do a little bit of rearrangement, again, our equation could be like this. You can see that we do have 2 VAs, or we do have 3 VAs, 3 VAs subtracted by VB equals, I have to move this 24 to another side. So it would be positive 24. At this point, I do have 5 VB subtracted by VA equals to negative 12. So everything is okay. As you guys know, we do have 3 ways in order to handle that. We do have the substitution method. We do have elimination method. We do have the matrix method. So at this point, I would prefer to use the substitution method because I can, for instance, write down the VA plus or VA based on VB or vice versa. So if I do that, I can say that my VA actually equals to 5VB plus 12. So I can put the VA inside of this guy. If I do that, my 3 times 5VB plus 12 subtracted by VB equals to 24. If you again rearrange this one a little bit more, what do you have? 3 times 5VB, you have to do expansion. 3 times 12, it would be 36, and I do have a negative VB. So it would be 15VB subtracted by VB, which is 14VB plus 36 equals to 24. If you rearrange this one, your VB would be equal to what? Your VB would be equal to negative 0.86 volts. So we found the VB. The only thing that we have to do right now is just put this VB inside any of the equations that I have, and I can find a VA. If I do that, my VA would be 7.7 volts. So far we do have anything that we need but related to the voltages. So what about, obviously, you have to make sure that your answer is right. It means that just put it inside any of the equation that you want, and you still have to get the same answer. So here's the question. Compute the current through the RAB. The direction is going to be A to the B. Let's see if that direction is going to be right or not. So VA is 7.7 volts, while VB is negative 0.8. So that makes sense because voltage all the time moves from positive to negative. So how I can find the current at that point? Let me use another color because it's going to get a little bit messy. So at this point, IB would be equals to VA subtracted by VB divided by R. So what do I have as VA? I do have it as 7.7 subtracted by negative 0.86 divided by 12. So your number could be something around 0.71 amp. So that's everything we need, right? Then it asks for compute the power in each resistor and check the power balance. Power balance which says that at this point, if you do have 2 current sources, the accumulation of all of those power that those guys are going to make, which obviously is going to be considered as negative, and it is some kind of the accumulation, you have to add it with all of the powers that these guys are going to consume should be 0. So let's see what would happen. At this point, I do have my current source, but I don't have the voltage. But since this guy is going to be in parallel with these 2 parts, I can say that at this point, I do have my V time. So I do have the voltage. The voltage of 3 ohm is going to be considered as the voltage of 1 amp. The voltage of 6 ohm is going to be considered as the voltage of 2 amp. At this point, we know that the voltage or the amount of power that both of these guys are going to produce is going to be negative. So instead of just worrying about if the voltage is positive or negative, I just consider that both of those voltages are going to be positive, multiplied by the related current, then just add a negative beside, and I can consider the accumulation of all of the powers are going to be negative. So let's see what would happen. So at this point, you're going to find the powers, right? Let's see. The power of 2 amp is going to be negative of V times I. What is the voltage? Voltage of 6 ohm is related to voltage of node A, as you can see over here. So it means that the voltage of node A was 7.7, and I have to multiply by what? I have to multiply by 2, which is around negative 15.4 watts. The power of 1 amp is still going to be negative V times I. So the voltage of 3 is going to be what? It's going to be negative 0.86, which is considered as positive, and multiplied by 1, which is going to be negative 0.86. So far I do have these two powers, but as the power that is going to be produced, right? If I add all of these powers plus, if I add all of these power to the power that are going to be consumed inside each resistor, I should find the zero. Rather than that, I made something wrong. So let's do it. The power of 12 ohm is going to be Ri squared. 12 times 0.7 to the power of 2. It is something around 6 watts. I rounded up, but don't worry. The power of 6 ohm is going to be, this since we do have the voltage, I can just use the V to the power 2 divided by R, which obviously is going to be positive because V to the power 2 is positive. So what is going to be 7.7 to the power 2 divided by 6. It's around 9.8 watts. And if you do the same thing with 3 ohm, the same thing, V to the power 2 divided by R, it's going to be my voltage to the power 2, 0.86 or 87 times 0.86 divided by 3. It's going to be what? It's 0.24. So here's the critical moment. If I add 24, let me just use another card. If I add 24 with 9.8 and with 6, I should have the accumulation of all of these two guys. So 15.4 plus 8.86 is going to be what? So let me just use another section. So the power of source should be equal to the power of R's. So what is the power of source is 15.4 plus 0.86, which is equals to what? It's around 16.3 watts. So the power of source, the power of resistors is 6 plus 0.24 plus 9.8 is equals to around 16 watt. As you guys know, we did a little bit rounding up that, so it's not that kind of a big difference. The only error that we have over here is less than 5 to 10%. So at this point, you guys just saw that by solving this equation and solving everything related to that using the case, we found out the voltages, the currents, and obviously the power. So maybe some of you would mention that it wouldn't be a little bit easier if we use this some kind of KVL at this point? Maybe, because the only consideration would be inside this KVL. We're only going to use the KVL inside the middle mesh rather than just all of those three. But in the future, you're going to see that by having more complicated and complex circuits, we still need to use the KCL itself, and that's way better. So let's see another challenge. At this point, we do have the supernode trigger. What does it mean with supernode? So let me give you an example. Imagine that you have something like this, 1.5 amp that gets inside one of the nodes. This is the node A, then we do have node B, and everything is normal. Blue, you do have one branch that the only thing that this guy has is a voltage source. So this guy is going to be a little bit challenging. Why? Because if I would like to write down the current that goes through this point or some kind of this point, I need a resistor, but this guy doesn't have any resistor by itself. So it means that VA subtracted by VB divided by what? And that guy is going to give me what exactly? So on that point, I'm going to have more amounts or more numbers, more number of unknowns, and I don't have enough equation. So at this point, we are going to consider something as the supernodes, means that instead of considering the fact that you do have only node A and B, you just consider the whole thing. You just consider the whole part and say that I'm going to consider this big one as one big node. And whatever current that gets in should be as the same as whatever current gets out. For instance, at this condition, whatever current that gets inside, which is 1.5 amp, should be as whatever current that gets outside. It still should be 1.5 amp, right? Because we are talking about the loop, and that completely makes sense. Maybe you guys would say that right now, so far, we only have one equation. What about another equation? Another equation is the relationship between your first node and the second node. As you can see over here, I do have the 10 volt, and 10 volt says the difference of the potential of voltages between node A and node B is going to be positive 10. By knowing these two factors, I obviously can do anything that I need. So let's go for it. Let's just solve this equation, or let's solve this question, because it's not that kind of challenging one. The only thing that you have to do right now is related to about the supernode. So let's do it. So I know for a fact that my current should be like this, that 1.5 amp should be the amount of current that moves outside of node B. So 1.5 amp, what should be node B, which is the VB subtracted by 0, which is the voltage of ground, divided by 8. Is that so? It means that simply my VB equals to 12 volts. As simple as that. Then I know another fact, that VA subtracted by VB is 10 volts. So if I rearrange that, my VA should be VB plus 10 would be 22 volts. Again, I do have everything that I need. Then what's the question? So the question from the supernode, and write down the KCL equations for it. So again, I talked about it. Use the consideration of VA subtracted by VB is going to be 10. We use that one. Find the current through the 10 volt source and its power delivered or absorbed. So as you guys know, since we are talking about the source, the power is going to be delivered, so it's going to be negative, but we still need to find the current, right? How we can do that? So at this point, we need another branch. We need this branch current. Why? Because since I don't know anything about some kind of resistance over here, by using the KCL based on this branch, I can find the current. One good thing I know about this branch is that the only thing that it has is just 4 ohm, and the voltage of that branch is going to be 10, because 10 volt is going to be in parallel with 4 ohm. So 10 divided by 4 is going to give me what? Is going to give me a number that I like, which is going to be what? 2.5. So I do have it as 2.5 amp. Let's just consider it that way. Let's consider it's going to be this way. So based on that, it means that a current should move from one point to another to produce 2.5 amp. Here's the important thing. What was the VB? The VB actually was what? Yeah, the VB was 12 and VA was 22. It means that the direction of current should be that way, right? Since the direction of the current should be that way, it means that the direction of the current in this branch also should be this way. Why? Obviously, it should be this way. We consider right, because VA is going to be bigger than VB. So based on that, I say that I1 equals to I4 plus I3. Don't worry about it. Right now, maybe some of you decided something is happening that we don't like. I still going to assure you that your equation is going to help you out in order to find the positive and negative sign. So based on that, 1.5 equals to what? I4. We found the I4 as 2.5 plus I3. So based on this fact, I3 would be equals to negative 1 amp. It means that the direction that we consider for I3 is not going to work on this point. The I3 actually was in this way, which made sense, right? Because most of the time, I tell you that current goes from negative to positive side of the voltage source. So my I3 is going to be negative if you are considered that specific direction that we have. But if I consider this direction, my I3 is going to be 1 amp. And that completely makes sense, because 1 amp plus 1.5 amp is going to be 2.5 amp. So let's find the power. The P equals to V times I. So at this point, I do have 12 volt, I have 10 multiplied by I, which is 1. So I do have it as 10 watts. Since it's going to be deliver the power, this power should be negative. So let's talk about the next challenge, the known voltage shortcut. So at this point, when you just look at the whole circuit, you can see that if I would like to go based on the KCL, I see 3 nodes, right? The node number 1, which is node A, node number B, and node C. But at this point, you do have a hint that you don't need even to find node B. Why? Because node B already connected to a voltage source and indirectly to the ground. So the only thing that is between your VB and ground is a voltage source. So obviously your VB is going to be 5 volt. From this point, I can move forward and say that, hey, I only need to find a KCL for A and C because I have the B. So I will have 2 unknown, 2 equations, and I can compute anything that I would like. So let's see what would happen over here. As I just told you, we consider that VA or node A is going to just reject all of those currents. And also the same thing is happening for C itself. So VA, let's talk about the case at A, is going to be what? It says that the I1, which is going to be V divided by 6 plus I2, which is going to be negative 2 amp, obviously because its direction is going to be opposite of 2 amps, plus V subtracted by 5 divided by 9 equals to 0. So at this point, you see that the KCL of part A is going to give us everything related to A itself. By just doing a little bit multiplication to get rid of the fractions, I can just simply find the VA. What about the KCL of part C? Because we need that. Just simply says VC subtracted by 5 divided by 12 equals to VC divided by 3. As simple as that. It means that by solving this one and this one, just by themselves, I don't need any extra thing. I can find VA and VC. So let's do it. For the KCL number 1, we do have VA divided by 6 is now subtracted by 2 plus this one is going to be 0. So we can find the LCD, or the least common denominator. It's considered as 18. If I multiply both sides by 18, I can get rid of fraction. So 18 by VA divided by 6 is going to be 3VA. 18 multiplied by negative 2, negative 36. 18 multiplied by VA subtracted by 5 divided by 9 is going to be 2VA subtracted by 10 equals to 0, right? So let's just casually simplify that. It means that it would be 5VA equals to what? 5VA equals to 46. If you find a value, VA would be 46 divided by 5, which is going to be around 15.2 volts. Then we are going to use this guy, right? Again, we have to multiply by the LCD. So at this point, we are going to multiply everything by 12. So if you do that, what do I got? I do have VC subtracted by 5 equals to 4 times VC. We rearrange that 5VC equals to 5, and VC is going to be equal to 1 volt. I do have 15.2 volt, and I do have 1 volt, and everything is still as simple as that. Obviously, VB was just 5 volt. So compute the current through 12 ohm, B to C, right? Where's the 12 ohm, B to C? The only thing I have to do is just subtract C by B, then divide it by 12. So what was B? B was 5, and C was 1 volt. So obviously, the direction should be this way. As I just told you, it doesn't matter which direction you're using for your currents. At the end, this equation is going to make everything fine. So the current for BC equals to divided by 12. It's going to be VB, which is what? VB equals to 5. Yes, because current to 5 volts subtracted by 1 divided by 12 is going to be 4 over 12. It is something around 0.33 amp. As simple as that. Then it says compute the total power delivered by the source and absorbed by resistors. I believe you can do it better than me. The only thing that you have to know is that the power that these two guys are going to deliver should be negative, and the power that everything is going to be consumed should be positive. As simple as that. So let's see another challenge, the multi-node supernode. As this position, as you can see, instead of just having one voltage source inside one branch, I do have two voltage sources back to back. So it means that instead of just considering one of these parts as supernode, I can simply consider the whole thing as a supernode. What does that mean? It means that my supernode would be from to here. So on that point, I do have my currents that are going to be rejected. This current and obviously this current. If I add all of them, it should be 0. What about the relationship between A and B and C? It's simple. I already know VA subtracted by VB is going to be 8. VB subtracted by VC is going to be 6. Let's do that. So at this point, as I just told you, we have to consider that all of the currents are moving out. So let's write down everything that I know. The case part A. It says that I don't have the KCL part A, to be honest. I only have one KCL because I only have one big supernode. So it would be V divided by 5 plus VB divided by 10 plus VC divided by 20 subtracted by 1 equals to 0. Is that so? Because as you know, I1 plus I2 plus I3 plus I4 is going to be 0. I4 is the opposite direction of 1 amp, so we do have this. Then we know a couple of more things. That VA subtracted by VB is equals 8 volts. VB subtracted by VC equals to 6 volts. So I do have 3 equations, 3 unknowns. Let's first of all get rid of all of the fractions. So LCD at this case is going to be 20. Let's multiply both sides by 20. So if I do that, 20 times VA divided by 5 is going to be 4VA. Same thing by VB divided by 10 is 2VB plus VC is going to be equal to 20. I just move the V, I just move the negative 1 and I multiply by 20 and just move it to another side. This is my first equation. The second one is that VA subtracted by VB, 8VB subtracted by VC is going to 6 volts. Again, it doesn't matter what way you use, but the one way that I'm going to use is about elimination. Because as you can see over here, the 2VB are going to be common over here between this equation and this equation. The only thing that would be different is about the sign. So by adding this to what? I do have VA subtracted by VC equals to 14. That is a good one. Why? Because I can use it some kind of anywhere that I like. It means that at this point, my VA is going to be 14 plus VC. This is one equation that I know. I already know that my VB equals 8 plus VC. This is another equation that I know. And I do have this equation that I already know. The only thing that you have to do is just put this one and this one. This one, which is just defined based on the VC there, and you can find the VC. When you find the VC, you can find a VB and you can find a VA. At the end of the day, you should have these numbers. It's going to be simple. It's not that kind of a hard and challenging thing.